Crystal field stabilization energy in octahedral complex. In octahedral complex, the d orbital of the metal cation are split into two sets of different energies, T2g of lower energy and Eg of higher energy. The separation between these two sets is equal to delta 0 equal to 10 dq. The T2g set has an energy of minus 0.4 delta 0 equal to minus 4 dq, and the Eg set has an energy of plus 0.6 delta 0 equal to plus 6 dq. Relative to the barycenter, minus and plus sign indicate decrease and increase in energy relative to the barycenter respectively. The complex ion with one electron in one of the T2g orbital has an energy of minus 0.4 delta 0 relative to the barycenter. This indicates that in a complex ion of D1 configuration of 0.4 delta 0 energy is released. This release energy is called the crystal field stabilization energy CFC of the complex ion. For D1 complex, electronic configuration is T2G1 Eg0. CFS is equal to minus 0.4 multiplied by 1 delta 0 equal to minus 0.4 delta 0. For D2 complex, electronic configuration is T2G2 Eg0. CFSC is equal to minus 0.4 multiplied by 2 delta 0 is equal to minus 0.8 delta 0. For D3 complex, electronic configuration is T2G3 E0. CFSC is equal to minus 0.4 multiplied by 3 delta 0 equal to minus 1.2 delta 0. For D4 high spin complex, electronic configuration is T2G3 EG1. CFSC is equal to minus 0.4 multiplied by 3 plus 0.6 multiplied by 1 delta 0 equal to minus 0.6 delta 0. Thus, for DN high spin complex with electronic configurations TP-T2G EGQ, CFSC is equal to minus 0.4 P plus 0.6 Q delta 0. Since no pairing of d electron occur in high spin complex, therefore no pairing energy is involved in CFSC. For low spin complex of D4, D5, D6, D7 metal ion, pairing of electron occur in T2G orbital. To pair up the two electron in an orbital, an extra energy is required, which is called as pairing energy P. Therefore, for D4 low spin complex, electronic configuration is T2G4 Eg0. CFSC is equal to minus 0.4 multiplied by 4 plus 0.6 multiplied by 0 delta 0 E plus P equal to minus 1.6 delta 0 plus P. For D5 low spin complex, electronic configuration is T2G5 Eg0. In this case, 4 electrons are forced to pair up in two different orbitals. T2G set CFSC is equal to minus 0.4 multiplied by 5 plus 0.6 delta multiplied by 0 in bracket delta 0 plus 2p equal to minus 2.0 delta 0 plus 2p. For Dn low spin octahedral complex with electronic configuration T2G-P-Eg-Q, CFSC is equal to minus 0.4 P minus 0.4 multiplied by P plus 0.6 multiplied by Q in bracket delta 0 plus MP, where P and Q are the number of electrons in T2G-Eg orbital respectively. M is number of pairs of electron caused by the ligand. P is the mean pairing energy. The required pairing energy is compensated from CFSC. Let us illustrate the difference in calculation of CFSC of some high spin and low spin complex. For D6 high spin electronic configuration is T2G4 Eg2. CFSC is equal to minus 0.4 P plus 0.6 Q delta 0 minus 0.4 multiplied by 4 plus 0.6 multiplied by 2 delta 0 is equal to minus 0.4 delta 0. In this case, no pairing energy is included because no pairing of an electron is caused by the ligand, though it has one pair of electron, but it is not caused by the ligand. This pair was already present in d orbital as shown below. One pair of electron dxy, dyz, dzx, dx square y square, dz square. In dxy, one pair of electron is present. For D6 low spin octahedral complex, the electronic configuration is T2G6 EG0. CFS is equal to in bracket minus zero point 0.4 multiplied by 6 plus zero point 0.6 multiplied by 0 bracket multiplied by delta 0 plus 2p. So equal to minus 2.4 delta 0 plus 2p. In this case, there are three pairs of electron, but only two are caused by ligand and one was already present in d orbitals. CO3 plus low spin 3d, T2G one pair from free metal cation, two pairs caused by strong ligand, e.g. the CFSC of D1 to D10 high spin and low spin complex are given. CFSC value for octahedral complex of D1 D10 metal cation system D1 arrangement of electron free metal cation will be 1. CFSC for high spin complex is not there. CFSC for D1 to D3 and D8 to D10 complex. So in T2G1 EG0, so minus 2.2 upon 5 delta 0. CFSC for low spin complex not there. In D2, 2 electron presence. CFSC for high spin complex not there. CFSC T2G to EG0, 2 electron present. So minus 4 upon 5 delta 0. CFSC for low spin complex is not there. Then D3, 3 electrons. T2G 3 EG0, 3 electrons present, minus 6 upon 5 delta 0. So high spin complex and low spin complex not present. Then D4, 4 electron present, T2G3 EG1. So 3 electron present in T2G, 1 electron present in EG. So value will be minus 3 upon 5 delta 0. And in low spin complex T2G4 EG0, so 4 electron will be present in T2G in low spin complex. Value will be minus 8 upon 5 delta 0 plus p. Then in D5, 5 electron present, so T2G 3 EG2 0 in high spin complex, but in low spin complex T2G5 EG0, it will all the electron will pair with each other. So value will be minus 10 upon 5 delta 0 plus 2p. This is CFSC for low spin complex. Then D6, 6 electrons, one pair electron is present. So T2G4 EG2. So CFSC in high spin complex, T2G 4 electron and EG 2 electron will be there. So value will be minus 2.5 delta 0. So in CFSC in low spin complex T2G6 EG1, 2 electron pair will be there. So a 3 electron pair will be there because all 6 electron present in T2G and 1 pair electron present in EG. So value will be minus 9.5 delta 0 plus p. In D7, 7 electrons are present. So in CFSC of high spin complex, T2G will have 5 electron, EG will have 2 electron. So value will be minus 4.5 delta 0. In T2G, 2 paired electron present and 1 unpaired electron, and in EG 2 unpaired electron is present. So the CFSC T2G6 EG2. So all 6 electrons are paired. That means in T2G 3 electron pair are there, and in EG 2 electron pair are there. So 6 minus 6 upon 5 delta 0. In D8, this is in the case of D8. T2G6 and EG2 will be there. Value will be minus 6 upon 5 delta 0. In D9, all the 9 electron will be there. So in T2G 6 electron will be pair. So 3 pair electron present, and in EG 3 electrons are there. That means 1 is pair electron, 1 is unpaired electron. Minus 3 upon 5 delta 0. Then in D10 all 10 electron pair. So T2G 6 electron will be there and EG 4 electron will be there. So value will be 0. Crystals feel stabilization energy in tetrahedral complex. In tetrahedral complex, the d orbital of the metal cation are split into two sets of different energy, electron of lower energy and T2 of higher energy. The separation between these two sets is equal to delta T. The E set has an energy of minus zero point 0.6 delta T and T2 set has an energy of plus zero point 0.4 delta T. Relative to the barycenter, for a Dn tetrahedral complex with E raised to P T2 raised to Q configuration in CFSC, minus zero point 0.6 P plus zero point 0.4 Q delta T will be there. So minus zero point 0.6 P plus zero point 0.4 Q is multiplied by 4/9 delta 0. So CFSC will be minus 0.27 P plus 0.18 Q delta 0. Why? Because delta T value is 4/9 delta 0. Since tetrahedral complex are high spin and no pairing of d electron occur, delta T is smaller than pairing, therefore no pairing energy is included in the above equation. The CFSC value of tetrahedral complex of D1 to D10 metal ion is given in table 4.7. In table 4.7, CFSC value for tetrahedral complex system D1, electronic distribution in E and D2 orbitals will be E1 T2 0. CFSC will be minus 0.27 delta 0. In system D2, electronic distribution in E and T2 orbital will be E square T2 0. CFSC will be minus 0.54 delta 0. D3 will be E2 T21 minus 0.36 delta 0. D4 will be E2 T22 minus 0.18 delta 0. In D5 E2 T23 it will be 0, and in D6 E3 T23 minus 0.27 delta 0. D7 will be E4 T23 minus 0.4 delta 0. In D8 E4 T24 minus 0.36 delta 0 will be there. In D9 E raised to 4 T25 minus 0.18 delta 0, and in D10 E raised to 4 T26, so value will be 0. Tetragonal distortion or Jahan-Taylor distortion. The 6 coordinates complex in which all 6 distance metal cations and the ligands are same and said to be regular octahedral complex. A complex will be regular octahedral when the electronic arrangement in T2G and EG orbital is symmetric. That is, both the T2G and EG orbital are electronically non-degenerate. It is because of the fact that symmetrically arranged electron will repel all the 6 ligands equally. When either T2G or EG orbitals are asymmetrically filled, that is, either T2G or EG orbitals are electronically degenerate, the regular octahedral geometry is not the stable, but it transforms into distorted octahedral geometry. The EG orbital point direct towards the ligand. Therefore, when EG orbital are electrically degenerate, that is unsymmetrically filled, some ligands are repelled more than others. Therefore, there is a significant distortion in octahedral complex. On the other hand, the T2G orbital lie in between the ligand. Therefore, the electronically degenerate T2G orbital cause a very small distortion. In general, the distortion that occurs in octahedral complex is a tetragonal distortion. A tetragonal distortion occurs when the two trans ligands on the z-axis in an octahedral complex, say Ml6, are moved either towards a metal ion or away from the metal ion or atom. Motion of the trans ligands along the z-axis towards the metal cation produce a tetragonal compression, and motion of this ligand away from the metal cation produce a tetragonal elongation. The shape of regular octahedral tetragonally compressed and tetragonally elongated complex are shown in figure 4.9. In A, regular octahedral is there. In B, tetragonal compressions is there, and in C, tetragonal elongations are there. So, the term tetragonal distorted is derived from the fact that When viewed along the z-axis, an octahedral complex looks like a tetragon. The condition which caused such a type of distortion was described by Jahn-Teller theorem. This theorem states that any non-linear molecule in an electronically degenerate state is unstable, and a molecule becomes distorted in such a way as to remove degeneracy, lower its symmetry, and lower the energy. The terms electronically degenerate that state refer to the situation in which an electron can be arranged in more than one orbitals of equivalent energy. This situation arises when the degenerate orbitals are unsymmetrically filled. For example, in octahedrally coordinated copper 2 plus ion Eg3 configuration is electronically degenerate because it has two possible arrangements of electron, that is D2x2y2 D1 dz2 or D1x2y2 D2z2. In dx2y2 2 electron will be there, in dz2 1 electron will be there, in dx2y2 1 electron will be there, and in dz2 2 electron will be there. Electronically degenerate states for Eg3 configuration. If there is only one possible arrangement of an electron, then this situation is called electronically non-degenerate. The D3, for example, configuration octahedral symmetry is non-degenerate, and symmetric. Only one arrangement is possible for the 3 electron, because it is not possible to put 2 electrons in one orbital, which violates the Hund's rule for maximum multiplicity. Single arrangement for D3 configuration. In regular octahedral field, the Eg orbitals, that is dx2y2 and dz2, are degenerate. However, if the Eg orbitals are asymmetrically filled, that is either dx2 y2 or dz2 orbital contain one electron more than the other, the Eg orbital are splits. If the dz2 orbitals contain one electron more than the dx2y2 orbital, then the ligand approaching along the z-axis will be repelled more than the ligand approaching along the x and y axis. It is because of the fact that electronically density in dz2 orbital is greater than that of dx2 y2 orbitals. Therefore, the ligand along the z-axis are moved away from the metal cation relative to those on x and y axis, which move forward towards the metal cation. The reason for distance between the metal cation and the ligand to be shorter on x and y axis is that the ligand repulsion is decreased as the ligand move away from the metal cation on z axis. Therefore, distance between the metal cation and the ligand on z axis become larger, and the distance between metal cation and the ligand on x and y axis becomes shorter. Thus, the complex undergo a tetragonal elongation, that is Z out distortion. Since the ligand on z axis are at larger distance from metal cation than that of the ligand on x and y axis, therefore the dz2 orbital will experience a decrease in repulsion from the ligand, and therefore the energy of dz2 orbital will decrease, and hence the dz2 orbital is stabilized. The dx2y2 orbitals will experience an increasing repulsion from the ligand, resulting in an increasing energy, and hence the dx2y2 will therefore be destabilized. With the barycenter remaining contained in a similar way, the energy of orbital having z component, that is dyz and dzx, will decrease, and that of x dxy will increase, and a part of degeneracy in the T2g orbital is removed. Therefore, the overall result is that the Eg orbital split into two levels, an upper dx2y2 and a lower dz2, and the T2g orbital is split into two levels, an upper dxy and a lower double degenerate dyz and dzx. The tetragonal elongation is generally called the tetragonal distortion and is observed in most of the tetragonal distorted complex. Crystal field splittings in tetragonal elongation Z out is shown in figure 4.10. If the dx2y2 orbital contains one electron more than the dz square orbital, then the ligand approaching along x and y axis will be repelled more than the ligand approaching along the z axis. It is because of the fact that electron density in dx2y2 orbitals is greater than that of dz square orbital. Therefore, the ligand along the x and y axis are moved away from metal cation, relative to those on z-axis which move towards the metal cation. The reason for the distance between the metal cation and the ligand to be shorter on z-axis is that the ligand-ligand repulsion is decreased as ligand move away from the metal cation on x and y-axis. Therefore, the distance between the metal cation and the ligand on x and y-axis become larger and become shorter on z-axis. Therefore, the complex undergo a tetragonal compression, that is Z is distortion. A degenerate d orbital is in free metal ion. In B, average energy of orbital in spherical crystal field, degenerate of d orbital in spherical field. In C, this d orbital of the phi d orbital will be split after consuming some energy. Splitting of d orbital in octahedral field. Then the in D, splitting of d orbital in tetragonal elongations, and in E, splitting of the orbital in square planar complex. So in this D section there will be tetragonal elongation, and in E section there will be square planar complex formation will be there. Since ligand on x and y axis are at the longer distance from metal cation than that of the ligand on z axis, therefore the dx square y square orbital will experience a decrease in repulsion from the ligand, and therefore energy of dx2y2 orbital will decrease. The dz square orbital will experience an increase in repulsion from the ligand and resulting in an increasing in energy, with the barycenter remaining constant. In a similar way, the energy of the orbital having x and y component dx orbital will decrease, and that of having z component, that is dyz and dzx, will increase. The crystal field splitting in tetragonal compression or Z in complex is shown in figure 4.11. Energy: d orbital in free ion, degenerate d orbital in free metal ion. B. Average energy of orbital in spherical crystal field, degenerate d orbital in spherical field. In C, splitting of d orbitals octahedral field, and in D, splitting of d orbitals in tetragonal compression. Since in tetragonal compression, 4 ligand on x and y axis repel the high density of electron in dx square y square orbital, whereas in tetragonal elongation only 2 ligands on z axis repel the high density of electron in dz square orbital. Therefore, there is more repulsion in tetragonal compression than that of tetragonal elongation. Therefore, tetragonal elongation is more stable than the tetragonal compression. Thus, tetragonal elongation is known as tetragonal distortions. The significant Jahan-Taylor distortion are generally observed in high speed D4 T2G3 EG1, low speed D7 T2G6 EG1, and D9 T2G6 EG3. Configuration in the octahedral geometry: because in this configuration Eg orbital are electronically degenerate and they point towards the high ligand directly. Some example of compound which undergo strong Jahan-Taylor distortion in octahedral field are CrF2 MnF3, D4 T2G3 EG1 NaNiO2, low spin D7 T2G6 EG1. Some copper 2 compounds such as copper difluoride, copper dichloride, copper dibromide, copper dichloride 4H2O, D9T263 EG3. In all these compounds, the metal cation are octahedrally surrounded by the ligands and Eg orbital are unsymmetrically filled. Therefore, there are 2 longer bonds on z-axis and 4 shorter bonds on x and y-axis. The Jahan-Taylor theorem does not predict which type of distortion will take place. Of nickel-2 complex surrounded by 4 strong and 2 weak ligands undergoes tetragonal distortion, but not due to Jahan-Taylor distortion, because Eg orbital, the dx2y2 and dz square are not electronically degenerate. the varying electrons repulsion between the non-equivalent ligands, and the d electron of the metal cation split the Eg orbital to a greater extent and T2G to a smaller extent.